Okay, so the next topic we're going to cover is mechanisms of acid-base interactions. So before we talk about what a mechanism is, let's just talk about a very generic acid-base reaction. So in Gen Chem, you're probably used to referring to generic acids as HA. I'm just going to take this and flip it to where the H is pointing to the right and the A is pointing to the left. No big deal. And so that's our generic acid, and we're going to have this generic acid interacting with a generic base. And just to be clear, this acid has a covalent bond between it. So this A and this H, these two atoms are covalently bonded to each other. And just to make this a tad bit simpler, let's go ahead and take this base and turn it into a negatively charged species. So go ahead and pause the video and try to predict what you would get on the right-hand side of the equation if the base interacted with the acid. Okay, so what you hopefully got was that if you have your acid interacting with the base is going to remove the hydrogen from the acid. So we'll end up getting this kind of a species where we have a conjugate base of our acid, and then we'll also get the conjugate acid of our original base. So if we really think about this, we need to do a couple of things. First thing is charge balance. So what we would see is that where the base began with a negative charge, our acid ends up with a negative charge in its conjugate base form. So let's go ahead and keep everything conserved, and now we have charge equality on both sides of the equation. But one thing you might not have really talked about too much in Gen Chem is the mechanics of what's actually going on. So this would be the way you would, write this balanced equation. You have charge balance, you have atom balancing, all that kind of stuff. But the actual mechanics of, how does that A get a negative charge? That might kind of have been glossed over a little bit. So this is where mechanisms come in. So we're going to try to use mechanisms as a way to really describe very specifically what's happening between the acid and the base. Okay, so to do that, we have to introduce a new kind of notation. So this is called ArrowNotation, where you can draw an arrow, something like this, to indicate flow of electrons. So whenever you draw an arrow like this, what's happening is you are basically telling your reader electrons are starting at the base of the arrow, and electrons are going to be stopping at the head of the arrow. So whenever you see the base of an arrow, you should always think to yourself, electrons start, and whenever you see the head of the arrow, you should always think electrons stop. Okay, so not only do we think start and stop, but we also think about making and breaking bonds. So one thing to always keep in mind is that for a covalent bond, you are generating that bond with electrons. Okay, so if you think about this H to B bond, this H over here on the right used to be this H on the left. So we have to have a way of notating that B and H are making a new bond. So the way we would do this is with the arrow notation. So we would designate the bond making by starting your arrow on the base, because the base has a free lone pair of electrons that it can use to make a new bond, and we're going to stop them on the hydrogen. Okay, so what's happening here is that the electrons from the base are starting here, and the electrons from the base are stopping on the hydrogen. So that start to stop relationship you can also think of it as a bond making process. Okay, and so if we just did this, we would have some kind of weird configuration where you have an A connected to an H connected to your base. And this would be very bad for a couple of reasons. The first of which is if you think back to our octet rules and our duet rules, we said that the hydrogen can never exceed the duet rule, or it can never have more than 2 electrons surrounding it at a time. So if you look at this hydrogen right here, we have a total of 4 hydrogens surrounding it. Okay, so because of that, this hydrogen 1 would be negative, but the point is that the hydrogen can actually not, it can never exceed the duet rule. So this kind of structure isn't going to be possible. So what we have to do to save ourselves from breaking the duet rule is we have to break this A to H bond. And the way we do that is we have to keep in mind that electrons are within that covalent bond, and we can also think about where the electrons go at the end of the day. So the electrons within this bond, if you look at this A over here on the right versus this A over here on the left, the conjugate base right here has another lone pair that it didn't have before. So the location that these are coming from are actually within this covalent bond. So we can actually break this bond and push electrons over to A. And so now you think about where these lone pairs, or where this lone pair came from. They're actually coming from the 2 electrons that are in this A to H bond. Okay, so this is the way that we notate bond making and bond breaking. So really another way to think about this arrow notation is not only electrons start and electrons stop, but you can also think of them as, you know, bond making and also bond breaking. Let's go ahead and do an example. So we're going to set up an acid-base reaction, and let's have it be between this acetic acid and between water. So we're going to have water and acetic acid. Let's go ahead and put some electrons around that oxygen. And so now I want you to go ahead and pause the video and try to predict, you know, what the products would look like on the right-hand side. And let's also try to draw the mechanism for how this would happen. So again, the mechanism is the full story of how we're actually making all of our bonds and how we're breaking all of our bonds. Okay, so it might have been a little bit difficult to figure out which of these species was going to be the acid and which of the species was going to be a base, just because both of them are neutral. And it's a little bit more difficult if you don't have a negatively charged species like up here to figure it out. So thinking back to the previous lecture, we had another example like this with the acetic acid and water. And just thinking about the name acetic acid, in this case, it's going to be kind of a giveaway. The acetic acid in this case will be the acid, and the water is going to be the base. So at the end of the day, one way we can draw this equilibrium is we could draw the negative charge going onto the oxygen, and we could end up showing a positive on the oxygen from the water. And so now we have to make sure we have charge neutrality or charge balance, and on the left-hand side of the equation we have neutral, net neutral, and on the right now we can double check and we can see we have a net neutral charge on the right. Okay, so since this is an equilibrium, let's go ahead and be a little bit more specific with our arrows. And so now we're going to have some kind of an equilibrium where this is going back and forth and back and forth. But now what we're going to do is try to draw the arrows to show, you know, how we're making bonds and how we're breaking bonds. And this is going to be something you'll do for the rest of your organic chemistry career, so this is actually a very important skill to develop. Okay, so what we're going to do is we're going to take one of the electron pairs, one of the lone pairs from the water. We're going to use those to make a new bond between the oxygen and this hydrogen right here. Okay, so again, electrons start, electrons stop, and then we can't just leave that be. If we did, we'd be breaking the duet rule. Okay, so a mantra we'll be saying over and over again is if you make a bond, you have to break a bond. If you make a bond, you have to break a bond. So since we've made a bond right here, we have to break a bond as well. Okay, so this is going to be our step for breaking a bond, and so we've made and we've broken. Okay, and so now let's pretend that if we were to go, you know, from these products, if we were to try to remake the starting material, how could we draw those arrows? Well, if you think about this molecule right here, this is the conjugate base of the carboxylic acid, and to go from left to right, he's lost a proton. So now that we're going to go from right to left, we're going to have to try to regain that proton for the carboxylic acid. So what we would do is we could, you know, draw our lone pairs for oxygen right here, and then we could use one of those lone pairs as a base and make a new bond between the oxygen and the hydrogen, and then we could break a bond between the hydrogen and the oxygen. And this would give us the left-hand side of the equation. So if we were going to draw electrons to go to the left, or draw an electron flow to allow us to go back to the left, these would be the arrows that would allow us to do that.